nearest star to our Sun has a name: Alpha Centauri. Just 4 light-years away, closer than any other star in the entire galaxy, it has called to us for centuries. And now, for the first time, the James Webb Space Telescope has turned its powerful eye toward this cosmic neighbor, searching for something that would change everything we know about our place in the universe. A world, a planet, perhaps a second home. If you find yourself settling in tonight for a peaceful voyage through the stars, consider tapping that like button and joining the Cosmic Drift family by subscribing. These journeys become even more meaningful when shared, and your support helps us continue exploring the wonders of the universe together. Alpha Centauri is not merely a star. It is a system, a cosmic family of 3 stars bound together by gravity in an ancient dance that has played out for billions of years. When you look up at the night sky from the southern hemisphere, you can see it with your naked eye, the 3rd brightest point of light in all the heavens, outshone only by Sirius and Canopus. But what appears as a single brilliant point contains mysteries that astronomers have only begun to unravel. The question that drives this search is both simple and profound. Could there be planets around these nearest stars? And if there are, could any of them harbor the conditions for life? This question has haunted humanity since we first looked up at the night sky and wondered if we were alone. For most of human history, this question remained purely philosophical. We had no way to detect planets around other stars. They were too small, too dim, too far away. The light from any planet would be completely overwhelmed by the blazing brightness of its parent star. Finding an exoplanet was like trying to see a firefly hovering next to a lighthouse from miles away while standing in broad daylight. But technology has changed everything, and in August of 2024, astronomers pointed the most powerful space telescope ever built at Alpha Centauri A, hoping to find what generations before them could only dream about. To understand what makes Alpha Centauri so special, we need to know what this stellar family looks like. The system consists of 3 stars. Alpha Centauri A is the largest, a yellow star almost identical to our own Sun. It is about 1.1 times the mass of our Sun and 1.5 times as bright. If you could stand on a planet orbiting Alpha Centauri A, the Sun in your sky would look almost exactly like the one we see from Earth. The color, the size, the warmth, it would all feel strangely familiar. Alpha Centauri B is the 2nd star, a close companion to A. It is an orange star, slightly smaller and cooler than our Sun, with about 90% of the Sun's mass and less than half its brightness. These 2 stars, A and B, orbit each other in a gravitational embrace that takes about 80 years to complete one full cycle. At their closest approach, they are separated by about 11 astronomical units, roughly the distance from our Sun to Saturn. At their farthest, they drift apart to about 36 astronomical units, similar to the distance from our Sun to Pluto. This binary dance creates a complex gravitational environment. Any planets orbiting either star must navigate the competing pulls of 2 stellar bodies. For decades, astronomers wondered if planets could even exist in such a system. The gravitational forces might tear apart any forming worlds, they thought, or fling them out into the cold darkness of interstellar space. The 3rd member of the family is Proxima Centauri, a small red dwarf star that is the closest individual star to our Sun. Proxima is tiny compared to its companions, with only about 12% of the Sun's mass and a fraction of a percent of its brightness. It orbits the binary pair at a vast distance, taking about 550,000 years to complete one orbit. Currently, Proxima lies about 13,000 astronomical units from the main pair, which is about 0.21 light-years. Despite its small size, Proxima Centauri has become one of the most studied stars in the sky. The reason is simple. In 2016, astronomers confirmed the existence of Proxima Centauri b, a planet orbiting in the star's habitable zone. This planet, roughly Earth-sized, became the closest known exoplanet to our solar system. The discovery electrified the scientific community and sparked renewed interest in the entire Alpha Centauri system. Proxima b orbits incredibly close to its parent star, completing one orbit in just 11.2 Earth days. It sits only about 4.8 million miles from Proxima Centauri, which is much closer than Mercury is to our Sun. But because Proxima is so dim, this close orbit places the planet in the habitable zone, where temperatures might allow liquid water to exist on the surface. The existence of Proxima b raises tantalizing possibilities, but also troubling questions. Proxima Centauri is a flare star, meaning it periodically erupts with intense bursts of radiation. These flares can be thousands of times more powerful than anything our Sun produces. A planet so close to such a volatile star would be bathed in radiation that could strip away its atmosphere and sterilize any surface life. There is also the matter of tidal locking. Because Proxima b orbits so close to its star, gravitational forces have likely locked one side of the planet to always face the Sun, just as our moon always shows the same face to Earth. This would create a world of eternal day on one side and eternal night on the other. The day side might bake while the night side freezes, unless an atmosphere thick enough to transport heat could moderate the extremes. We have confirmed that Proxima Centauri hosts at least 2 planets, with a third candidate still under investigation. Proxima d, confirmed in 2022 and independently verified in 2025, is a small world that orbits even closer to the star than Proxima b. It completes one orbit in just 5.1 days and is among the lightest exoplanets ever detected. A third possible planet, Proxima c, has been proposed but remains controversial, as the signals that hinted at its existence may have been artifacts in the data. But while Proxima Centauri has captured much attention, the larger stars of the system, Alpha Centauri A and B, have proven far more challenging to study. These sun-like stars are so bright that any planets orbiting them are completely overwhelmed by their light. The techniques that work for detecting planets around dim red dwarfs struggle when applied to brilliant yellow and orange stars. This is where the James Webb Space Telescope enters the story. Webb is not like any telescope that came before it. Launched in December 2021, it carries a primary mirror more than 21 feet across, composed of 18 hexagonal gold-plated segments. This mirror collects infrared light from the universe with unprecedented sensitivity, allowing Webb to see things that no previous telescope could detect. For hunting planets around bright stars, Webb carries a special tool called MIRI, the mid-infrared instrument. Within MIRI are coronagraphs, devices that act like artificial eclipses. They block out the light from a star, allowing astronomers to see the much fainter objects that might be orbiting nearby. Think of it like holding up your hand to block the sun so you can see something just next to it. A coronagraph does this with exquisite precision, blocking starlight while allowing planet light to pass through. The mid-infrared wavelengths that MIRI observes are particularly useful for planet hunting. At these wavelengths, the contrast between a star and its planets is much more favorable than in visible light. Planets are warm, and they glow in the infrared. While a planet might be billions of times fainter than its star in visible light, at mid-infrared wavelengths, that ratio drops dramatically. Sure. A young, warm planet might only be thousands of times fainter than its star, which is still challenging but potentially within reach. In August 2024, a team of astronomers led by researchers from Caltech pointed Webb's MIRI instrument at Alpha Centauri A. This was one of the most challenging observations ever attempted with the telescope. Alpha Centauri A and B are so bright that they can overwhelm instruments. They also move across the sky faster than almost any other stars, which complicates observations. The operations team had to develop a custom observing sequence just for this target. The team placed a coronagraphic mask over Alpha Centauri A, blocking its intense light. But complications immediately arose. The nearby presence of Alpha Centauri B added extra brightness that seeped into the images. Light bends around the edges of coronagraphs, creating ripples and patterns in the surrounding space. The telescope's own mirrors and support structures cause light to interfere with itself, producing circular and spoke-like patterns that can easily be mistaken for planets. To deal with this, the team employed sophisticated image processing techniques. They created models of all the contaminating light, both from Alpha Centauri A and from the nearby Alpha Centauri B. By subtracting these models from the original images, they performed a digital cleanup that revealed what might be hiding in the star's glare. What emerged from this process was a faint point of light. The researchers called it S1, a source 10,000 times fainter than Alpha Centauri A, sitting at a distance of about twice the Earth-Sun separation from the star. The detection was clear enough that the team could not easily dismiss it as an artifact. But astronomers are trained skeptics. They know that instruments can produce false signals, that cosmic rays can create spurious detections, that background galaxies can masquerade as nearby objects. The team subjected their data to rigorous testing. Could this be a glitch in Webb's optics? Could it be a distant galaxy that happened to appear in the right spot? Could it be stray light bouncing around inside the telescope? None of these explanations quite fit. The object appeared too consistent, too well defined to be an artifact. Background galaxies at this wavelength should have been detectable in other ways, but no such source appeared in the relevant catalogues. The researchers published their initial findings, but they knew they needed more data to be certain. Follow-up observations came in February and April of 2025. But when the team looked at these new images, something unexpected happened. The object had vanished. Where S1 had appeared so clearly in August 2024, there was nothing but the familiar patterns of coronagraphic noise. This disappearing act might seem like evidence that the original detection was a mistake. But the researchers had another explanation. If the object is a planet on an elliptical orbit, it would not always be visible. Sometimes the planet would be at a position in its orbit that Webb could detect. Other times, the planet would move too close to the star, lost in the coronagraph's blocking zone, or pass behind the star where it would be completely hidden. To test this hypothesis, the team ran millions of computer simulations. They modeled possible orbits that would be consistent with seeing the planet in August 2024, but missing it in the 2025 observations. They also had to account for the gravitational influence of Alpha Centauri B, which would destabilize certain orbits and fling planets out of the system entirely. The results were intriguing. About half of the simulated orbits that fit all the data placed the planet in a position where it would have been invisible to Webb during the February and April 2025 observations. The planet would have been too close to the star, hidden in the glare that even the coronagraph could not completely eliminate. there was also an intriguing connection to older data. Back in 2019, the European Southern Observatory's Very Large Telescope had observed Alpha Centauri A and detected a puzzling signal. At the time, astronomers could not confirm whether it was a real planet or an artifact. When the Webb team incorporated this 2019 data into their models, it strengthened the case that something was orbiting Alpha Centauri A. Based on all the available evidence, the researchers estimated what this potential planet might be like. They believe it could be a gas giant with a mass similar to Saturn, orbiting Alpha Centauri A in an elliptical path that varies between 1 and 2 astronomical units from the star. This elliptical orbit would carry it through most of the star's habitable zone. If confirmed, this would be a remarkable discovery. It would be the closest directly imaged planet to a Sun-like star ever detected. It would be the most similar in temperature and age to the giant planets in our own solar system. And it would be our nearest neighbor, sitting just 4 light years away. But confirmation remains elusive. As one researcher noted, all data, whether it is a detection or not, tells you something. Even if this candidate turns out to be something else, the observations have demonstrated the true capabilities that Webb's instruments can push toward. The search continues. Future observations with Webb will attempt to catch the planet at different points in its orbit. NASA's Nancy Grace Roman Space Telescope, set to launch by May 2027, carries advanced coronagraph technology that may be able to see planets Webb cannot. Ground-based extremely large telescopes now under construction will also join the hunt. But while we wait for confirmation around Alpha Centauri A, we must also consider what we already know about Proxima Centauri b, the planet we are certain exists. This world has been the subject of intense study since its discovery in 2016, and what we have learned paints a complex picture of what habitability might mean around a red dwarf star. Proxima b sits in what astronomers call the habitable zone, that region around a star where temperatures are just right for liquid water to exist on a planet's surface. This is sometimes called the Goldilocks zone, not too hot, not too cold. But the term can be misleading. Being in the habitable zone does not guarantee a planet is habitable. It simply means one basic requirement for life as we know it might be met. For Proxima b, the challenges begin with its parent star. Proxima Centauri is a red dwarf, a type of star that burns its fuel slowly and can shine for trillions of years. This longevity might seem promising for life. Earth-like life took billions of years to develop here, so a star that lasts 1 trillion years provides plenty of time for evolution to work. But red dwarfs come with serious drawbacks. They are small and dim, which means their habitable zones are very close in. Proxima b orbits only 7.5 million kilometers from its star, which is about 20 times closer than Earth is to the Sun. At this distance, gravitational forces have almost certainly locked one face of the planet toward the star permanently. One hemisphere bakes in eternal day, while the other freezes in eternal night. Early models suggested this tidal locking would be catastrophic for habitability. The atmosphere would freeze out on the night side, they predicted, collapsing into glaciers of frozen air. But more recent research has shown that this might not be the case. An atmosphere with sufficient density, perhaps containing carbon dioxide or other greenhouse gases, could transport heat from the day side to the night side effectively enough to prevent collapse. In fact, the terminator zone, that twilight band between eternal day and eternal night, might provide the most stable conditions. Here, temperatures would be moderate, sheltered from the extremes of both sides. If liquid water exists on Proxima b, this is where it might be found. A more serious challenge comes from Proxima Centauri's flares. Red dwarfs are often flare stars, prone to sudden, violent outbursts of radiation. Proxima Centauri is no exception. Studies using the ALMA radio telescope have detected hundreds of flare events, some releasing enormous amounts of energy in just seconds. These flares produce intense ultraviolet and X-ray radiation, potentially sterilizing any surface life. The radiation problem is worsened by the planet's likely lack of a strong magnetic field. Earth's magnetic field, generated by the churning of molten iron in our core, deflects much of the harmful radiation from the Sun. But Proxima b rotates very slowly, if at all, due to tidal locking. This slow rotation may prevent the planet from generating a strong magnetic field, leaving its atmosphere and surface exposed. Scientists have modeled what this radiation bombardment would do to an Earth-like atmosphere. The results are concerning. Extreme ultraviolet radiation can ionize atmospheric gases, stripping electrons away and allowing the atmosphere to erode into space. One study found that Proxima b receives about 30 times more extreme ultraviolet radiation than Earth, and 250 times more X-rays. Over billions of years, this assault could have stripped away any water the planet started with. When the star was young, before Proxima Centauri settled into its current state, it was even more luminous. Any planet in what is now the habitable zone would have been much closer to the star relative to its energy output. Water on the surface would have evaporated, and the vapor could have been split into hydrogen and oxygen by ultraviolet light. The hydrogen, being light, would have escaped into space, taking the planet's water with it. This scenario, called atmospheric escape, may have left Proxima b as a desiccated world, perhaps with an atmosphere thick with oxygen but devoid of water. Some models suggest that even if the planet retained its atmosphere, the oceans may have boiled away during this early period. Yet not all hope is lost. There are scenarios where Proxima b could have retained water and developed conditions suitable for life. If the planet formed farther out and migrated inward after the star's turbulent youth, it might have avoided the worst of the radiation. Or it might have started with much more water than Earth, enough to survive the losses. Some researchers have proposed that a thick hydrogen envelope early in the planet's history could have protected a volatile-rich core. This hydrogen layer would have absorbed the extreme ultraviolet radiation during the pre-main sequence phase, when Proxima Centauri was most dangerous. Later, the hydrogen would have escaped, leaving a world that could potentially support surface oceans. The only way to resolve these questions is through direct observation. We need to determine whether Proxima b has an atmosphere, and if so, what that atmosphere contains. Or the James Webb Space Telescope has the capability to do this, though it is extremely challenging. By observing the planet as it passes in front of and behind its star, astronomers can analyze the light filtering through or reflecting off any atmosphere, searching for the chemical fingerprints of water, oxygen, carbon dioxide, or methane. But Proxima b presents a particular difficulty. We have not been able to confirm that it transits its star, passing directly between Proxima Centauri and Earth. Without transits, the standard method of atmospheric analysis does not work. Alternative techniques exist, such as measuring thermal phase curves as the planet rotates. But these are at the edge of what current technology can achieve. The story of Alpha Centauri is ultimately a story about the search for home. Not just a habitable planet, but a place that resonates with something deep in the human spirit. When we look at these nearest stars, we are looking at possibilities, asking whether we are alone in the universe and whether there might be places we could someday reach. The distances involved are still staggering. 4 light-years sounds close in cosmic terms, but it translates to about 25 trillion miles. With current spacecraft technology, a journey to Alpha Centauri would take tens of thousands of years. The Voyager 1 probe, the fastest object humans have ever launched, would need about 73,000 years to cross this distance. But there are those who dream of reaching the stars much sooner. In 2016, a project called Breakthrough Starshot was announced, backed by technology billionaire Yuri Milner and supported by the late Stephen Hawking. The concept is audacious. Instead of traditional rockets, Starshot proposes using powerful lasers to push tiny spacecraft across interstellar distances. The plan calls for building a massive array of ground-based lasers, perhaps millions of individual units working together, that could focus 100 gigawatts of power onto a light sail. This sail, thinner than a human hair and only a few meters across, would be attached to a spacecraft no larger than a microchip. Under the intense laser pressure, this tiny craft would accelerate to about 20% of the speed of light in just 10 minutes. At that velocity, the journey to Alpha Centauri would take only about 20 years. 4 years later, any images or data collected during the flyby would reach Earth, carried by weak but detectable radio signals. Within a single human lifetime, we could see the first close-up images of planets around our nearest stellar neighbors. The technical challenges are immense. The sail material must be incredibly light, yet survive acceleration forces 40,000 times greater than Earth's gravity. It must also remain reflective while allowing some laser light to pass through, preventing it from vaporizing under the beam's intensity. The spacecraft itself must fit everything: cameras, power supply, communications, and navigation, into a package weighing less than a gram. Scientists have been working on these problems. Researchers at Caltech have made the first experimental measurements of laser-induced motion on miniature light sails. Materials scientists are exploring exotic substances like silicon nitride that might survive the punishing acceleration. Engineers are developing ways to pack entire spacecraft onto chips smaller than a coin. But a recent report suggests the project has lost momentum. The initial $100 million in funding has been largely spent on research, and the path forward remains unclear. Some critics argue that the project is simply too far ahead of current technology. Building a laser array powerful enough to push light sails to 20% of the speed of light would require advances in multiple fields that may be decades away. Still, the dream persists. Even if Breakthrough Starshot never launches a single probe, the research it has funded has pushed the boundaries of what we think is possible. Sometime, perhaps not in our lifetimes, but perhaps not too far in the future, humanity may send its first emissaries to another star. And if we do, Alpha Centauri is the obvious destination, not just because it is closest, though that matters enormously when travel times are measured in decades, not just because we already know it hosts planets, but because the Alpha Centauri system contains stars so similar to our own Sun that any planets around them might feel almost like home. Imagine, for a moment, what it would be like to approach Alpha Centauri from interstellar space. The system would first appear as a single bright point, growing slowly brighter over years of travel. Eventually, the point would split into two, as Alpha Centauri A and B resolved into separate stars. A third, much fainter point would be Proxima Centauri, glowing red in the distance. As your spacecraft approached, you would see the binary pair performing their stately dance, orbiting each other once every 80 years. The yellow light of Alpha Centauri A would look achingly familiar, so similar to the sunlight that bathed your distant home. The orange glow of Alpha Centauri B would cast a warmer hue, like perpetual sunset. And somewhere among these stars, perhaps a planet, a world orbiting in the habitable zone, warmed by sunlight so like our own. Perhaps a world with oceans and atmosphere, clouds and rain. Perhaps even life, looking up at the same stars we see, wondering if anyone was out there. We do not yet know if such a world exists. The candidate planet around Alpha Centauri A remains unconfirmed. Proxima B may be a radiation-blasted wasteland or a world sheltered by thick clouds. But the search continues, driven by that most human of questions. Are we alone? The James Webb Space Telescope will keep watching. Future telescopes, both in space and on the ground, will join the search. And with each observation, each data point, each analysis, we get closer to an answer. Tonight, as you settle into sleep, Alpha Centauri is there, hanging in the southern sky. The same light that left those stars 4 years ago is reaching your eyes now, having crossed the void between us at the fastest speed the universe allows. That light carries the heat of nuclear fusion, the signature of stellar atmospheres, and perhaps, reflected from some unseen planet, the subtle clues to another world. The cosmos is vast beyond imagining, but Alpha Centauri is right next door, our nearest neighbor in an infinite neighborhood, and we are finally learning to see what has always been there, waiting for us to look. The science of detecting exoplanets has evolved dramatically over the past 3 decades. When astronomers first confirmed the existence of planets around other sun-like stars in 1995, it was a revolutionary moment. That first detection, a hot Jupiter orbiting the star 51 Pegasi, was found using the radial velocity method. Scientists watched for the tiny wobble a planet induces in its host star as the two bodies orbit their common center of gravity. This method has proven remarkably successful, revealing thousands of exoplanets. It was the technique that confirmed Proxima Centauri B in 2016. Astronomers at the European Southern Observatory spent years collecting data, watching for that telltale wobble in Proxima Centauri's motion. When they announced the discovery, they had measured a periodic signal corresponding to an 11.2-day orbit, consistent with an Earth-mass planet in the habitable zone. But radial velocity has limitations. It tells us about a planet's minimum mass and orbital period, but nothing about the planet's size, atmosphere, or surface conditions. More importantly for bright stars like Alpha Centauri A, the technique struggles when stellar activity creates noise in the data. Stars are not smooth, glowing spheres. They have spots and flares and convective motions that can mimic or mask the signal of an orbiting planet. The transit method has become equally important. When a planet passes directly between its star and our line of sight, it blocks a tiny fraction of the star's light. By measuring this dimming precisely, astronomers can determine the planet's size relative to its star. The Kepler Space Telescope used this method to discover thousands of exoplanets, revolutionizing our understanding of how common planetary systems are in the galaxy. Yet transit detection requires precise alignment. A planet must pass directly across the face of its star as seen from Earth. For most planetary systems, this alignment does not occur. Proxima B, for instance, does not transit its star, which has limited what we can learn about it through indirect methods. Direct imaging represents a different approach entirely. Instead of inferring a planet's presence from its effects on the star, direct imaging seeks to capture light from the planet itself. This is extraordinarily difficult because stars are so much brighter than the planets around them. In visible light, a Jupiter-like planet might be 1 billion times fainter than its parent star. Seeing such a planet would be like spotting a single birthday candle next to a 1,000,000-watt searchlight. The mid-infrared wavelengths that Webb's MIRI instrument observes make this easier. At longer wavelengths, planets are relatively brighter compared to their stars. A warm planet glows in the infrared, emitting light based on its own temperature rather than just reflecting starlight. The contrast ratio drops from billions to mere thousands, which is still challenging but potentially achievable with sophisticated instruments. Coronagraphs are essential tools for this work. The concept dates back to 1930, when French astronomer Bernard Liot invented the first coronagraph to study the sun's corona without waiting for an eclipse. By blocking the bright disk of the sun, Liot could observe the faint outer atmosphere that is normally invisible against the day sky. Modern coronagraphs are far more sophisticated. They must block starlight with extraordinary precision, while allowing light from nearby planets to pass through. Different designs achieve this in different ways. Some use opaque masks to physically block the star. Others use phase masks that alter the wave properties of incoming light, causing destructive interference that cancels out the starlight. The MIRI instrument on Webb carries 4 coronagraphs. 3 are 4-quadrant phase mask coronagraphs, designed for observing at 10.65, 1140, and 1550 micron wavelengths. The 4th is a classical Liot coronagraph operating at 23 microns. Each is optimized for different observing scenarios, allowing astronomers to choose the best tool for their target. The 4-quadrant phase masks work by dividing the incoming light into 4 quadrants and shifting the phase of the light in alternating quadrants by half a wavelength. When the light recombines, the starlight interferes destructively with itself, effectively cancelling out. Planet light, coming from a slightly different angle, does not experience this cancellation and can pass through. This technique provides an incredibly small inner working angle, which is the closest to the star that a planet can be detected. The inner working angle for the MIRI phase mask coronagraphs is about 1 lambda over d, where lambda is the wavelength of light and d is the telescope diameter. This means they can see closer to a star than most other coronagraph designs. When the Webb team observed Alpha Centauri A, they used the coronagraph at 1550 microns. At this wavelength, the inner working angle corresponds to detecting objects about 0.5 arcseconds from the star. At Alpha Centauri's distance of 4.3 light-years, this translates to being able to see planets orbiting at distances of about 1 astronomical unit or more from the star. But even with a coronagraph, significant challenges remain. Starlight leaks around the edges of any mask, creating residual patterns that must be subtracted. The telescope's own structure causes diffraction spikes, lines of scattered light that radiate outward from any bright point source. And any imperfections in the telescope's mirrors create speckles, bright spots that can be mistaken for planets. To deal with these issues, astronomers use reference star subtraction. They observe a nearby star similar in brightness to their target, using exactly the same instrument configuration. This reference star observation captures all the same artifacts and patterns, but without any planets. By subtracting the reference observation from the target observation, many of these artifacts cancel out, revealing what is truly present around the target star. The Alpha Centauri observations required additional complications. Because Alpha Centauri A has a close companion star, Alpha Centauri B extra light contaminated the images. The team had to model and subtract not only the coronagraphic residuals from the target star, but also the scattered light from its binary companion. The data processing chain is complex. Raw images from the telescope first undergo detector-level corrections, accounting for the quirks and imperfections of the infrared sensor. Then background light from the sky and telescope is subtracted. The coronagraphic PSF, the point spread function showing how light from the star spreads across the detector, must be carefully modeled using sophisticated algorithms. Finally, careful statistical analysis determines whether any detected point sources are real planets or merely residual noise. For the August 2024 observations, this processing revealed the candidate object S1. It appeared clearly in the processed images, 10,000 times fainter than Alpha Centauri A itself. The separation from the star corresponded to about 2 astronomical units, placing it in a region where planets could have stable orbits despite the gravitational influence of Alpha Centauri B. The disappearance of this object in subsequent observations has created what the researchers call the case of a disappearing planet. But this is not necessarily evidence against the planet's existence. Consider how different a planet would look at different points in its orbit. If the candidate planet orbits in an ellipse, as most planets do, its distance from the star varies over time. Sometimes it would be at apastron, its farthest point from the star, where it would appear most separated from the coronagraph's blocking zone, and thus most detectable. At other times, it would approach periastron, its closest point, where it would be lost in the residual glare near the coronagraph mask. Furthermore, an orbiting planet does not always appear to one side of its star. Sometimes it appears to the left, sometimes to the right, and sometimes it passes directly in front of or behind the star from our viewing angle. When behind the star, it would be completely invisible. When in front, it would be lost against the star's brightness. The team's modeling explored millions of possible orbits consistent with the detection in August 2024, the non-detection in February and April 2025, and the earlier 2019 observations. They found that about half of these orbits placed the planet in a position where it simply could not be seen during the 2025 observations, regardless of how sensitive the telescope was. If the planet exists, it is likely a gas giant with a mass comparable to Saturn. This conclusion comes from analyzing the brightness of the object in the mid-infrared images. The brighter an object appears at these wavelengths, the larger and warmer it must be. The detected signal corresponds to something that radiates like a planet with several hundred Kelvin surface temperature, which is consistent with a Saturn mass world at that orbital distance around a sun-like star. The existence of such a planet would be surprising in some ways and expected in others. Giant planets are common in the universe. Studies of exoplanets have shown that many, perhaps most stars, host planetary systems. But the particular configuration of a Saturn mass planet orbiting at 1 to 2 astronomical units around a binary star system is unusual. The gravitational environment created by 2 orbiting stars places constraints on where planets can exist. Computer simulations of planetary formation and stability in binary systems show that planets can survive only in certain regions. Very close to either star, the gravitational influence of the companion is weak, and planets can form and remain stable. Very far from both stars, beyond where the binary's combined gravity fades to irrelevance, planets can also exist. But in between, the competing gravitational pulls create chaos, ejecting any forming planets into interstellar space. For Alpha Centauri, These constraints are severe. The binary orbits with a separation that varies from 11 to 36 astronomical units. Any planet orbiting either star must stay well within a few astronomical units to remain stable. The candidate planet, at about 2 astronomical units, would be near the outer edge of stability around Alpha Centauri A. Perhaps more concerning for those hoping to find habitable worlds, the candidate planet's orbit passes through most of Alpha Centauri A's habitable zone. A Saturn-mass gas giant has no solid surface where life could develop, but its presence would have profound implications for any smaller planets in the system. Gravitational perturbations from a giant planet sweep through its orbit like a broom. Smaller planets that venture too close are likely to be flung out of the system or sent crashing into the star. If the candidate planet's orbit truly extends from 1 to 2 astronomical units, it may have cleared out the very region where an Earth-like world might otherwise have formed. This would be disappointing news for those who dream of finding a second Earth around the nearest Sun-like star. But it would not be the end of the story. Moons of giant planets can themselves be habitable. In our own solar system, the moons Europa, Enceladus, and Titan show evidence of conditions where life might exist. A Saturn-like planet in the habitable zone of Alpha Centauri, AEA, might host moons with liquid water oceans beneath icy shells. Furthermore, the candidate planet may not be the only planet in the system. Our own solar system contains dozens of significant bodies, including 4 terrestrial planets, 4 giant planets, and numerous dwarf planets and moons. Alpha Centauri A might host a rich planetary system of its own, with smaller worlds orbiting inside the giant planet's reach. Future observations will help resolve these questions. The research team plans to continue observing Alpha Centauri A with Webb, hoping to catch the candidate planet at different points in its orbit. If they can detect it multiple times over the coming years, they will be able to map out its orbital path precisely, determining its mass and trajectory with much greater accuracy. The Nancy Grace Roman Space Telescope, scheduled to launch by 2027, carries an experimental coronagraph instrument specifically designed for direct imaging of exoplanets. Roman will be able to observe invisible light wavelengths where current ground-based coronagraphs struggle. While it may not be able to match Webb's sensitivity in the infrared, it could potentially detect planets that appear at different phases of their orbits. Ground-based extremely large telescopes are also entering the scene. The European Extremely Large Telescope, with a primary mirror 39 meters across, is under construction in Chile. The Giant Magellan Telescope and the 30-meter telescope are planned for similar capabilities. These massive instruments, equipped with advanced adaptive optics that correct for atmospheric distortion in real time, may be able to directly image planets that space telescopes cannot. The combination of multiple instruments observing at different wavelengths and times offers the best chance for confirmation. Each telescope sees the universe slightly differently. A detection consistent across multiple instruments and observation epochs becomes increasingly difficult to dismiss as a fluke. Beyond mere detection, astronomers hope eventually to characterize any planets around Alpha Centauri in detail. Characterization means learning about a planet's atmosphere, its composition, its temperature structure, perhaps even signs of surface conditions or weather. For Proxima b, which we know exists but cannot easily observe directly, this prospect remains tantalizingly out of reach. Atmospheric characterization typically relies on spectroscopy, breaking light into its component wavelengths to identify the chemical fingerprints of different molecules. Each gas absorbs light at specific wavelengths, leaving dark lines in a spectrum that reveal its presence. By analyzing light that has passed through or reflected off a planet's atmosphere, astronomers can determine what that atmosphere contains. The most exciting prospect is the detection of biosignatures, chemical signs of life. On Earth, the atmosphere contains oxygen, methane, and ozone in combinations that would be difficult to maintain without living processes. If we could detect similar combinations on an exoplanet, it would be strong evidence that something is producing these gases, possibly something alive. But biosignature detection is extraordinarily difficult. The signals are incredibly faint, buried in noise and contaminated by the host star's own light. Current instruments can just barely detect atmospheres around the largest exoplanets orbiting the smallest stars. For Earth-sized planets around Sun-like stars, we are years or decades away from the necessary technology. The Alpha Centauri system presents both opportunities and challenges for atmospheric characterization. On one hand, its proximity makes any signals from planets there much stronger than from more distant systems. On the other hand, the bright stars overwhelm faint planetary signals, and the lack of transits around the larger stars limits which techniques can be applied. For Proxima b specifically, Webb has already attempted atmospheric observations. Initial results have been inconclusive, unable to confirm or rule out the presence of a substantial atmosphere. The tiny planet's signal is simply too faint, and Proxima Centauri's flares add noise that complicates interpretation. The situation may improve as observations accumulate. Astronomers can stack data from multiple observations, averaging out random noise while retaining consistent signals. Over time, faint features may emerge from the fog of uncertainty, but progress is slow, measured in years of careful work rather than dramatic discoveries. This patience is built into astronomy. Darchigi. The universe reveals its secrets reluctantly, requiring sustained effort and creative thinking. The discovery of Proxima b itself came only after years of monitoring, with early hints appearing as far back as 2013, but confirmation not arriving until 2016. The candidate planet around Alpha Centauri A may follow a similar timeline, with years of follow-up needed before we can say with confidence whether it is real. The human investment in this search is substantial. The James Webb Space Telescope cost nearly $10 billion and took more than 2 decades to develop. Thousands of scientists and engineers from dozens of countries contributed to its construction and operation. Each observation of Alpha Centauri represents not just telescope time, but the accumulated expertise of generations of researchers. Why do we spend such resources looking at nearby stars? The answer touches on something fundamental about human nature. We are explorers, driven by curiosity to understand the world around us. The question of whether life exists elsewhere in the universe ranks among the most profound we have ever asked. Finding an answer, even a partial one, would change how we see ourselves and our place in the cosmos. There is also a practical dimension. If humanity is ever to become a truly spacefaring civilization, we will need to understand what awaits us among the stars. The nearest star systems are the first stepping stones beyond our solar system. Learning what planets exist there, what conditions they present, what resources they might offer, is essential preparation for any future exploration. The Alpha Centauri system is the most accessible target for interstellar study. At 4 light years, it is close enough that we can already see details in its light that would be invisible from more distant stars. Future telescopes may be able to map the surfaces of planets there with resolutions comparable to what Galileo saw through his first telescope, when he looked at our own moon. And if Breakthrough Starshot or a successor project ever succeeds in sending a probe, Alpha Centauri will certainly be the destination. No other star system offers such a favorable combination of proximity and scientific interest. Whatever we learn from remote observation paves the way for eventual direct exploration. The search for planets around Alpha Centauri also advances our understanding of planetary systems in general. Each new discovery helps calibrate our theories of how planets form, how they evolve, and how common various configurations might be. By studying our nearest neighbor, we learn about the possibilities for worlds throughout the galaxy. We now estimate that most stars in the Milky Way host planets, red dwarfs like Proxima Centauri, which make up about 75% of all stars, frequently have small rocky planets in their habitable zones. Sun-like stars often host systems of multiple planets, including both rocky worlds and gas giants. The galaxy teems with worlds, perhaps 100 billion in our Milky Way alone. Yet despite this abundance, we have not found another Earth. We have found planets of similar mass and planets in habitable zones, but never both together around a sun-like star close enough for detailed study. The closest we have come is Proxima b, which orbits a flare star so different from our Sun that comparisons are difficult. Alpha Centauri A offers the best chance to find a world truly like our own. If planets exist there, they receive light nearly identical to Earth's sunlight. Their years would be similar in length. Their climates would be shaped by the same basic physics that governs our weather. A habitable world around Alpha Centauri A would be the most Earth-like planet we know. The search has intensified recently because the technology has finally become capable. Webb's observations represent a new frontier in direct imaging. The coronagraphs work better than expected. The telescope's stability exceeds requirements. For the first time, we can peer into the glare of nearby sun-like stars and glimpse what might be orbiting there. Whether the candidate planet around Alpha Centauri A proves real or not, the observations themselves represent a triumph. They demonstrate that direct imaging of planets in the habitable zones of nearby sun-like stars is becoming possible. They show the path forward for future instruments and missions. They bring the dream of finding another Earth tantalizingly close. The universe does not owe us an Earth-like planet around Alpha Centauri. The formation of planetary systems involves chaos and chance, with outcomes determined by the particular collisions and gravitational interactions that occurred billions of years ago. Perhaps the binary nature of Alpha Centauri A and B prevented Earth-sized planets from forming in stable orbits. Perhaps such planets formed but were destroyed or ejected. Perhaps they exist, but have not yet been detected. What we can say with certainty is that the search continues. Each observation adds to our knowledge. Each null result narrows the possibilities. Each detection, confirmed or tentative, points toward new avenues of investigation. The story of Alpha Centauri is still being written. Tonight, as you drift toward sleep, consider what a remarkable time this is to be alive. For thousands of generations, humans looked at the stars and could only wonder what was there. Now, within our lifetimes, we are beginning to see not just points of light, but worlds. Not just stars, but solar systems. Not just distances, but destinations. The nearest star calls to us across 4 light years of void. It has called to every generation that has ever looked up at the night sky. Though they did not know its name or understand its nature, we are the first generation that can truly answer that call, reaching out with our instruments to see what has always been there hidden in the light. The journey to Alpha Centauri begins not with spacecraft, but with knowledge. We must first understand what awaits us before we can dream of going there. And that understanding grows with each passing year, each new observation, each hard-won insight into the nature of the universe. Perhaps someday our descendants will visit these worlds. Perhaps they will stand beneath the light of Alpha Centauri A and look up at our own sun, now just another star in their sky. Perhaps they will walk on shores we can only imagine, breathing air we have only theorized, seeing landscapes we have only dreamed. Or perhaps Alpha Centauri will remain forever unreachable, a neighbor we can observe but never visit. Even then, the search has value. Knowledge is its own reward. Understanding where we fit in the cosmos, whether we are alone or part of a vast family of inhabited worlds, shapes how we see ourselves and each other. The stars do not care whether we look at them. They shine regardless, their fusion fires burning steadily across time spans that dwarf human history. But we care. We are the universe's way of knowing itself. As Carl Sagan once said, every observation, every analysis, every discovery adds to that knowing. Alpha Centauri waits, as it has waited for billions of years. The search for worlds continues, and in the searching, we find meaning. The question of habitability haunts every discussion of exoplanets. We throw the word around freely: habitable zone, potentially habitable, habitability criteria. But what do we really mean? The answer is more complex than it might seem, and nowhere is this complexity more apparent than in the Alpha Centauri system. Habitability, in its most basic definition, refers to the potential for a world to support liquid water on its surface. Water is the foundation of all life we know. Every living organism on Earth requires water. Even the hardiest extremophiles, bacteria that thrive in boiling hot springs or frozen Antarctic ice, depend on liquid water at some point in their life cycles. Without water, the chemistry of life as we understand it simply does not work. This focus on water leads directly to the concept of the habitable zone, that orbital region around a star where a planet's surface temperature allows liquid water to exist. Too close to the star and water boils away into steam. Too far and it freezes into permanent ice. Only in the narrow zone between these extremes can oceans persist. For our Sun, the habitable zone extends roughly from the orbit of Venus to the orbit of Mars. Earth sits comfortably in the middle, while Venus, slightly closer, has succumbed to a runaway greenhouse effect that has baked its surface to temperatures hot enough to melt lead. Mars, slightly farther, lost most of its atmosphere early in its history and is now a frozen desert. But the habitable zone is not a guarantee. Venus is within the inner edge of our Sun's habitable zone, yet it is clearly not habitable. Mars is near the outer edge, yet we do not find flowing rivers there today. The habitable zone is necessary but not sufficient for habitability. Other factors matter enormously. Atmosphere is perhaps the most important. A planet needs enough atmospheric pressure to prevent liquid water from immediately evaporating or sublimating into space. It needs greenhouse gases to trap heat and regulate temperature. It needs a composition that does not poison the chemistry of life. Earth's atmosphere, with its nitrogen, oxygen, carbon dioxide and water vapor, provides all these things. But achieving such an atmosphere requires a complex history of planetary evolution. Planets do not simply appear with comfortable atmospheres already in place. Atmospheres form from volcanic outgassing, delivery by comets and asteroids, and chemical reactions with surface materials. They can be stripped away by stellar radiation, by giant impacts, by the solar wind. They can transform chemically over time, as Earth's atmosphere did when photosynthetic life began producing oxygen billions of years ago. For planets around red dwarf stars like Proxima Centauri, atmospheric survival is a major concern. Red dwarfs are dim, which means their habitable zones lie very close in. At these short distances, planets are subject to intense stellar winds and ultraviolet radiation that can erode atmospheres over time. The numbers are sobering. Proxima b receives about 30 times more extreme ultraviolet radiation than Earth. During stellar flares, which occur frequently on active red dwarfs, this exposure can spike to thousands of times Earth's levels. Such intense radiation ionizes atmospheric gases, stripping away electrons and creating plasma that can be swept away by the stellar wind. A planet needs protection against this onslaught. Earth's magnetic field provides a shield, deflecting charged particles around the planet, rather than letting them impact the atmosphere directly. Without our magnetosphere, Earth would likely have lost much of its atmosphere long ago, as Mars apparently did when its magnetic field died. Generating a magnetic field requires a churning liquid metal core. On Earth, the combination of our planet's rapid rotation and the convective motion of iron in our outer core creates a dynamo effect, generating the magnetic field that protects us. But tidally locked planets rotate very slowly, if at all. Proxima b likely always shows the same face to its star, just as our moon always shows the same face to Earth. This slow rotation may prevent the formation of a strong magnetic dynamo. Some models suggest that alternative mechanisms could provide protection. A thick atmosphere might shield the surface even without a magnetic field, absorbing radiation before it reaches the ground. If the planet has an intrinsic magnetic field even weaker than Earth's, it might still provide some protection. Certain atmospheric compositions might be more resistant to erosion than others. The truth is, we do not know whether Proxima b has retained an atmosphere. The calculations that predict atmospheric loss make many assumptions about the planet's initial volatile inventory, its magnetic field strength, and its atmospheric composition. Different assumptions lead to wildly different conclusions, ranging from complete atmospheric erosion to the retention of a substantial atmosphere. Only direct observation can resolve these questions. If we can analyze light from Proxima b, either through transit spectroscopy or direct imaging, we can determine what gases are present. The detection of water vapor would be particularly significant. If the planet has retained water in its atmosphere despite billions of years of stellar radiation, it would suggest that habitable conditions might be possible. The challenge of observing Proxima b illustrates a broader problem in exoplanet science. We can detect planets far more easily than we can characterize them. The radial velocity method that found Proxima b tells us the planet exists and provides its minimum mass and orbital period. But it tells us nothing about the planet's size, density, atmosphere, or surface conditions. For that, we need additional observations that are often at the very edge of current capabilities. Transit observations offer the most detailed characterization, but only for planets that pass directly in front of their stars as seen from Earth. This geometric requirement excludes most planetary systems. For Proxima b specifically, extensive searches have failed to detect transits, suggesting the planet's orbit is inclined such that it never crosses the star from our perspective. Direct imaging is the alternative, but current instruments cannot directly see Proxima b. The planet is too small, too close to its star, and too faint compared to the stellar glare. Future telescopes may change this. The extremely large telescopes now under construction, with mirrors tens of meters across, may be able to directly image Earth-sized planets around the nearest stars, but these instruments are still years from completion. In the meantime, we piece together what information we can. We model different scenarios, exploring what conditions might exist on Proxima b and how we might detect them. We compare to analogous planets in our own solar system and to other exoplanets we have studied. We make predictions and design observations to test them. This scientific process, hypothesis, prediction, observation, revision, drives our understanding forward even when definitive answers remain elusive. Each study narrows the range of possibilities. Each observation adds another data point. Slowly, incrementally, the picture clarifies. The situation is different for Alpha Centauri A, where direct imaging is actually becoming possible. The candidate planet detected by Webb is far enough from its star that current coronagraphs can potentially see it. If confirmed, this planet will become one of the most intensively studied objects in astronomy. A Saturn-mass planet in the habitable zone of a Sun-like star would be fascinating in its own right. Such planets are not common in our solar system's habitable zone. Jupiter and Saturn orbit far beyond the snow line, where ice condensed during the early solar system and allowed them to grow massive. Finding a giant planet closer in suggests a different formation history, or a history of orbital migration. Migration occurs when planets form at one location in a disk of gas and dust, but then move to a different orbit through gravitational interactions. Giant planets can migrate inward, pushed by interactions with the gas disk, or scattered by encounters with other planets. Our solar system's Jupiter may have migrated inward and then outward during its history, shaping the formation of the inner planets. If the candidate planet around Alpha Centauri A migrated to its current position, it may have disrupted any smaller planets that once existed in the habitable zone. This process, sometimes called orbital instability, can create chaotic periods in a planetary system's history where worlds collide, merge, or are ejected entirely. Alternatively, the planet may have formed more or less where we see it now. Some models of planet formation suggest that giant planets can form relatively close to their stars if enough solid material accumulates quickly. The presence of Alpha Centauri b in the system complicates these models, as its gravitational influence would affect the disk from which planets formed. Understanding this one planet's history connects to broader questions about how planetary systems form and evolve. Every new system we study adds to our sample, improving the statistics that underpin our theories. The Alpha Centauri system is particularly valuable because of its proximity, which allows more detailed observations than we can achieve for more distant targets. Beyond the planet itself, there is the question of moons. In our solar system, the giant planets host dozens of moons each. Some of these moons are as large as small planets. Titan, orbiting Saturn, has a thick atmosphere and lakes of liquid methane on its surface. Europa and Enceladus harbor subsurface oceans of liquid water kept warm by tidal heating. If the candidate planet around Alpha Centauri A hosts similar moons, those moons could be habitable. A Europa-like moon in the habitable zone of a Sun-like star would receive warmth both from tidal heating and from the star's radiation. Such a world might support liquid water oceans beneath an icy shell, protected from the harsh radiation environment by kilometers of frozen water. Detecting exomoons is even harder than detecting exoplanets. The signals are smaller, the techniques less developed. But as our instruments improve, this frontier will eventually open. If we confirm a giant planet around Alpha Centauri A, the search for its moons will follow. The broader context of the Alpha Centauri search involves our changing understanding of where life might exist. For most of human history, we assumed life required conditions much like Earth's: a rocky surface, liquid water oceans, an atmosphere, sunlight for energy. The habitable zone concept emerged from this thinking, focusing on the range of orbital distances where Earth-like conditions might prevail. But life on Earth has proven far more adaptable than we once imagined. Deep beneath the ocean, communities of organisms thrive around hydrothermal vents, drawing energy from chemical reactions rather than sunlight. Microbes live kilometers underground, in the pores of solid rock, surviving on the chemical gradients between different mineral compositions. Life has colonized every environment on Earth that provides liquid water and an energy source, regardless of how extreme those environments might seem. This expanding definition of habitability has led to new targets in our search for life. The icy moons of the outer solar system, once dismissed as too cold and dark for life, now rank among the most promising places to look. The subsurface oceans of Europa and Enceladus could harbor ecosystems similar to those at Earth's deep sea vents. Even Titan, with its liquid methane lakes and complex organic chemistry, might support some form of exotic life. Applied to exoplanets, this broader view opens new possibilities. A planet outside the traditional habitable zone might still be habitable if it has internal heat from radioactive decay or tidal forces. A planet with a thick hydrogen atmosphere might stay warm far from its star through greenhouse effects stronger than we typically consider. A rogue planet drifting through interstellar space, ejected from its birth system long ago, might sustain life in a subsurface ocean heated by its own internal energy. None of this means we abandon the search for Earth-like planets in traditional habitable zones. Such worlds remain the most promising targets for finding life, especially life we might be able to detect remotely. The biosignatures we know how to look for, oxygen, ozone, methane in disequilibrium, are based on Earth's example. Detecting similar signatures on an exoplanet would be the strongest possible evidence for life. But the search has expanded. We now consider a wider range of environments where life might exist, and we work to develop methods for detecting signs of life in those environments. The Alpha Centauri system, with its multiple stars and multiple potential planetary configurations, offers a laboratory for exploring these possibilities. The psychological dimension of this search deserves attention as well. The question of whether life exists elsewhere touches on deep human concerns about meaning, purpose, and our place in the universe. For some, the discovery of extraterrestrial life would be profoundly exciting, evidence that we are part of a vast cosmic community. For others, it might be troubling, challenging assumptions about human uniqueness or religious beliefs. Throughout history, discoveries that changed our cosmic perspective have had cultural impacts far beyond science. Copernicus and Galileo's revelation that Earth orbits the Sun rather than the reverse shook medieval certainties to their foundations. Darwin's theory of evolution transformed how we understand our own origins. The discovery of the vast age and size of the universe in the 20th century humbled our sense of scale. Finding life around another star would belong to this tradition of transformative discoveries. It would answer a question humans have asked for as long as we have been human. It would confirm that the processes that led to life on Earth are not unique, that the universe is capable of generating living things wherever conditions permit. And it would raise new questions about the nature of that life, its history, its intelligence, its awareness of us. Even without finding life, the search for habitable planets shapes how we think about our world. Learning what conditions are necessary for habitability highlights how remarkable Earth is. Understanding how rare or common habitable planets are informs our sense of cosmic loneliness or connectedness. Seeing our own world in the context of other worlds deepens our appreciation for what we have. The Alpha Centauri system offers a particularly poignant case because of its proximity. If we find a habitable planet there, it will be our nearest neighbor, close enough that we can imagine someday visiting. If we find that no habitable planets exist in this nearby system, it suggests that Earth-like worlds may be rare even when conditions seem favorable. Either answer changes our understanding. The search for planets around Alpha Centauri also connects to practical concerns about humanity's long-term future. Earth will not be habitable forever. In roughly 1 billion years, the sun will have brightened, enough to boil away our oceans, ending the conditions that support complex life. In 5 billion years, the sun will swell into a red giant, consuming or destroying the inner planets entirely. If humanity or our descendants are to survive these timescales, we will eventually need to leave Earth. The Moon, Mars, and the outer solar system offer potential homes for the next few centuries or millennia. But truly, long-term survival may require spreading beyond our solar system entirely. Alpha Centauri, as the nearest star system, represents the first step on that journey. This is not a concern for our generation, or even our civilization. The timescales involved dwarf human history. But the decisions we make now, the knowledge we accumulate, the technologies we develop, all contribute to possibilities that our descendants may one day realize. The search for habitable planets around nearby stars is part of that legacy. Of course, reaching Alpha Centauri remains a distant dream. The distances involved are almost impossible to grasp intuitively. 4 light-years sounds modest compared to the billions of light-years that span the visible universe. But it translates to about 25 trillion miles, a distance so vast that our fastest spacecraft would need tens of thousands of years to cross it. Light itself, traveling at 186,000 miles per second, takes more than 4 years to make the journey. Any signal we send to Alpha Centauri, traveling at the speed of light, would arrive 4 years later. A reply would take another 4 years to return. Communication with even our nearest stellar neighbor involves delays longer than many human endeavors. Physical travel is incomparably harder. Chemical rockets, the workhorses of current spaceflight, top out at speeds of a few tens of kilometers per second. At these speeds, reaching Alpha Centauri would take more than 100,000 years. Nuclear rockets could do somewhat better, but still require many millennia. Only speculative technologies like antimatter propulsion or light sails pushed by powerful lasers offer any hope of interstellar travel within a human lifetime. The breakthrough starshot concept pushes the boundaries of what might be achievable. By accelerating tiny spacecraft to 20% of the speed of light using ground-based lasers, Starshot aims to reach Alpha Centauri in just 20 years. The technical challenges are enormous, requiring advances in laser technology, materials science, communications, and miniaturization. But the physics is sound, and research continues despite funding uncertainties. Even if Starshot succeeds, the capabilities of such tiny spacecraft would be limited. A chip-sized probe cannot carry the sophisticated instruments of a mission like Webb. It would at best capture a few images and measurements during a high-speed flyby, transmitting them back to Earth over subsequent years. But those images would be the first ever taken from another star system, an achievement that would mark a new era in human exploration. For now, we must content ourselves with remote observation. Telescopes like Webb push the boundaries of what we can see from Earth orbit, detecting planets and characterizing atmospheres across interstellar distances. Future missions will push these boundaries further. The Roman Space Telescope, the extremely large ground-based observatories, propose space missions with even larger mirrors and more sophisticated instruments, all promise to reveal new details about nearby planetary systems. The pace of discovery has accelerated remarkably. The first exoplanet around a sun-like star was confirmed only in 1995. Today we know of more than 5,000 confirmed exoplanets, with thousands more candidates awaiting verification. We have found planets smaller than Earth and larger than Jupiter. We have found planets orbiting two stars at once and planets that orbit no star at all. We have found planets closer to their stars than Mercury is to our Sun, and planets farther out than Pluto. This explosion of discoveries has transformed our understanding of planetary systems. We now know that planets are common, that most stars host at least one planet, that the diversity of planetary configurations exceeds what our own solar system suggested. The cosmos teems with the worlds of every conceivable type. Yet for all this abundance, we still lack the one planet we most want to find, a true Earth twin, a rocky planet of similar mass and size to Earth, orbiting in the habitable zone of a sun-like star, with an atmosphere that allows liquid water on its surface. We have found planets that check some of these boxes, but never all of them at once for a nearby, well-characterized target. Proxima b comes close. It is rocky, roughly Earth-sized, and orbits in its star's habitable zone. But Proxima Centauri is a red dwarf, not a sun-like star. The conditions on Proxima b would be profoundly different from Earth, with constant radiation bombardment, probable tidal locking, and a dim red sun that never sets on one hemisphere. Alpha Centauri A offers the chance to find something more Earth-like. The star itself is almost identical to our Sun. If a rocky planet exists in its habitable zone, that planet would experience conditions remarkably similar to Earth's. The sunlight would have the same color and intensity. The years would be a similar length. The day-night cycle could be normal if the planet is not tidally locked. The candidate giant planet, if confirmed, suggests the possibility of such a world is reduced but not eliminated. A Saturn mass planet does sweep through the habitable zone, but smaller planets might exist in stable orbits closer to the star or farther out. We cannot rule out the existence of an Earth-like world until we have surveyed the system thoroughly. The technology to perform such a survey is approaching. Within the next decade, combinations of space telescopes and ground-based observatories should be able to detect Earth-sized planets in the habitable zones of the nearest stars, if such planets exist. The discovery of such a world would be one of the most significant scientific findings in history. Imagine the headlines that would follow confirmation of an Earth-like planet around Alpha Centauri A. After millennia of wondering, we would finally know that our cosmic neighborhood contains another world where the conditions for life exist. The philosophical and cultural implications would ripple through society for generations. Of course, finding an Earth-like planet is not the same as finding life. A planet might have all the right conditions but remain lifeless, either because life never arose or because it was destroyed by some catastrophe. Confirming the presence of life would require additional observations, detecting biosignatures in the planet's atmosphere, or someday, direct investigation by interstellar probes. The search for biosignatures is itself a frontier of astrobiology. We know what atmospheric gases life on Earth produces, but we do not know if alien life would produce the same signatures. Alternative biochemistries might generate different waste gases. Some potential biosignatures could also be produced by non-living processes, creating false positives. The field is developing new methods and frameworks for interpreting whatever signals we eventually detect. What we can say with confidence is that the search is worthwhile. Whether we find life, find only lifeless worlds, or find ambiguous signs that require further investigation, we will learn something important about our place in the universe. The process of searching focuses human curiosity and ingenuity on one of the deepest questions we can ask. The answer, whatever it turns out to be, will be worth knowing. As night deepens and the stars wheel overhead, Alpha Centauri traces its path across the southern sky. To most people who see it, the star is just another point of light, indistinguishable from the thousands of others that dot the heavens. But to those who know, it represents something extraordinary. Our nearest stellar neighbor, a cosmic front porch just 4 light years away. The light reaching your eyes tonight left those stars just over 4 years ago. In that time, spacecraft have orbited distant planets. Telescopes have captured new images. Scientists have published new studies. The universe has changed, and so has our understanding of it. Yet the stars continue their ancient light, oblivious to our efforts to comprehend them. This tension between cosmic timescales and human timescales defines much of astronomy. The stars operate on billions of years. We live for decades. The distance to Alpha Centauri is 4 light years. We have been seriously searching for exoplanets there for less than a decade. Our entire scientific civilization is a brief flash in the history of the cosmos. Yet in that flash, we have learned more about the universe than all previous generations combined. The search for planets around Alpha Centauri is part of this accelerating quest. Each observation builds on those that came before. Each discovery opens new questions. Each generation of scientists carries the work forward, standing on the shoulders of those who came before while reaching toward answers that may come only after they are gone. Tonight, somewhere in the world, a telescope is pointed at Alpha Centauri. Perhaps it is Webb, collecting infrared light for some observing program. Perhaps it is one of the great ground-based observatories, its adaptive optics fighting the shimmer of Earth's atmosphere. Perhaps it is an amateur with a backyard telescope, simply enjoying the view of our nearest stellar neighbor. All of these observers are connected by a common thread of curiosity. The professional astronomer analyzing data, the student learning to reduce observations, the amateur sketching star fields in a notebook, all are asking the same fundamental questions. What is out there? Are we alone? What does the universe hold beyond what we can see? Alpha Centauri does not answer these questions on its own. It is simply a star system, doing what star systems do, burning hydrogen, radiating light, dragging whatever planets it may have through their orbits year after year. The questions arise from us, from minds that evolved on a small planet around an ordinary star in an unremarkable corner of the galaxy. But the answers, if they come, will come from out there, from light that has traveled across the void, carrying information encoded in its wavelengths and intensity. From the faint signals of distant worlds, barely distinguishable from noise but real nonetheless. From the patient accumulation of data that slowly resolves uncertainty into knowledge. The James Webb Space Telescope is our most powerful tool for this work, but it will not be the last. Already, plans are underway for its successors. The technologies that make Webb possible, large lightweight mirrors, infrared sensors, precise coronagraphs, will be refined and extended in future missions. Each generation of telescopes sees farther, sees clearer, sees more. Whether we find a habitable planet around Alpha Centauri in the coming years or the coming decades, the search will continue. The question of life beyond Earth is too important, too profound, to abandon regardless of early results. And the Alpha Centauri system, by virtue of its proximity, will always be a prime target for investigation. Perhaps, in a future not too distant, we will know what planets orbit Alpha Centauri A and B. Perhaps we will have measured their atmospheres, determined their temperatures, assessed their potential for life. Perhaps we will even have images of their surfaces, maps of their continents and oceans, if continents and oceans they have. Or perhaps Alpha Centauri will disappoint us, revealing a system hostile to life, with no habitable planets and no moons where conditions might be favorable. This too would be an answer, a data point in our quest to understand how common habitable worlds are in the universe. Whatever the outcome, the search changes us. It expands our horizons, deepens our humility, sharpens our appreciation for the conditions that allow life to exist. The very act of looking outward, of asking whether anyone else is out there, affirms something essential about human nature. We are beings who seek understanding, who reach beyond our immediate circumstances toward larger truths. The stars wait, as they have always waited. Alpha Centauri shines on year after year, eon after eon. And we, the curious creatures who have only recently developed the means to ask our questions, continue the search. In the grand scheme of the cosmos, our efforts are vanishingly small. A handful of telescopes, a few thousand researchers, a thin stream of data. Against the vast indifference of space and time, it seems almost absurd that we should imagine ourselves capable of answering the biggest questions. And yet, each observation adds to our knowledge. Each discovery reshapes our understanding. Each generation carries the work forward. The questions that seem unanswerable today may have answers tomorrow. The frontiers that seem impassable may one day be crossed. The night is long, but not forever. Dawn will come, as it always does, bringing new light to a world that has spent another night turning beneath the stars. And somewhere, in that new day, another observation will be made, another analysis completed, another step taken on the long road toward understanding. Alpha Centauri awaits. The search continues, and the universe, vast and old and strange, slowly reveals its secrets to those patient enough to look. The moment of discovery, when it comes, is rarely what people imagine. There is no dramatic revelation, no sudden flash of insight, no orchestral swell. Instead, there is data, numbers in spreadsheets, patterns in noise, months of analysis, checking and rechecking, ruling out alternatives one by one. The team that detected the candidate planet around Alpha Centauri A experienced this quiet kind of discovery. When they first processed the August 2024 observations, a faint point appeared in the coronagraphic images. It could have been anything: an artifact, a cosmic ray, a distant galaxy. The researchers did not immediately believe they had found a planet. Instead, they began the painstaking process of elimination. They tested whether the signal could be an instrumental artifact by examining how it behaved across different exposures and different processing techniques. An artifact would typically show some inconsistency, appearing and disappearing in ways that did not match a real astronomical source. The signal remained consistent. They checked whether it could be a background object. Distant galaxies can appear as point sources at infrared wavelengths, and some happen to lie along the line of sight to nearby stars. But the expected density of such sources at this brightness level made a chance alignment unlikely. Moreover, certain characteristics of the signal, such as its color and lack of extended structure, argued against a galactic origin. They considered whether the signal might be scattered light from Alpha Centauri b, the companion star that complicates observations of the system. Scattered light can create artifacts that mimic point sources, especially near the edge of a coronagraph's blocking zone. But the researchers had carefully modeled and subtracted the contribution from both stars, and the signal persisted. After exhausting the obvious alternatives, the team concluded that the signal was likely a real astronomical object associated with Alpha Centauri A. Given its brightness and separation from the star, the most plausible interpretation was a planetary companion. But even this tentative conclusion came with caveats and uncertainties. Science is built on skepticism. Every claim must be scrutinized, every conclusion challenged. The researchers published their findings not as a confirmed discovery, but as a candidate detection, explicitly acknowledging the need for follow-up observations. They knew that the history of exoplanet science includes false alarms, signals that seemed promising at first, but later turned out to be artifacts or misinterpretations. The follow-up observations in early 2025 added a new twist to the story. The candidate signal was not present in the February or April data. For some, this might seem to invalidate the original detection. If it was a real planet, why did it disappear? But the researchers had anticipated this possibility. An orbiting planet does not stay in the same apparent position relative to its star. It moves along its orbit, sometimes appearing well separated from the star, and sometimes hidden close to it or behind it. If the August 2024 observation happened to catch the planet near the optimal part of its orbit for detection, while the 2025 observations caught it at less favorable positions, the non-detection would be entirely consistent with a real planet. This interpretation required modeling the possible orbits of such a planet. Not just any orbit would work. The orbit had to be consistent with the observed separation and brightness in August 2024, the non-detection in early 2025, and the constraints imposed by the gravitational influence of Alpha Centauri b. Only orbits that satisfied all these requirements were viable. The modeling revealed that about half of the viable orbits placed the planet in positions where it would have been undetectable in the 2025 observations. This is not definitive proof that the planet exists, but it shows that the non-detection is consistent with its existence. Additional observations at different times will help distinguish between orbits that predict detection and orbits that predict non-detection, gradually constraining the possibilities. The researchers also incorporated a fascinating historical data point. In 2019, astronomers at the European Southern Observatory observed Alpha Centauri A using a different technique and instrument. They detected a signal that could have been a planet, but the detection was never confirmed. At the time, it was considered intriguing, but inconclusive. When the Webb team compared their 2024 detection with the 2019 data, they found that some orbital solutions could explain both observations. A planet on the right kind of orbit would have appeared in roughly the positions indicated by both the 2019 and 2024 detections, while being at unfavorable positions during the 2025 observations. This consilience of independent datasets strengthened the case that something real was being detected. However, the 2019 data alone was not sufficient to confirm the planet. The earlier observation used different wavelengths and different techniques, making direct comparison difficult. The error bars on the position and brightness of the 2019 signal were large enough to accommodate a range of interpretations. It remained possible that the 2019 and 2024 signals were unrelated, each a separate artifact or noise fluctuation that happened to be roughly consistent. This ambiguity is frustrating but unavoidable at the frontier of observational capability. The Alpha Centauri observations push Webb's instruments to their limits. The coronagraphs are designed to suppress starlight by factors of thousands, but residual light still creates a complex pattern that must be carefully characterized and removed. The slightest imperfection in this removal can create spurious signals. Moreover, Alpha Centauri is a particularly challenging target. The two main stars are so bright that they can saturate detectors, producing artifacts that propagate through the data processing pipeline. Their rapid motion across the sky complicates observations that require precise pointing. The presence of two bright stars in close proximity creates scattered light that must be modeled and removed. The Webb operations team developed special procedures for observing Alpha Centauri. They designed a custom sequence of exposures that accounted for the system's unique characteristics. They tested these procedures on other targets before applying them to Alpha Centauri itself. Despite these precautions, the resulting data required more careful processing than most Webb observations. This level of effort reflects the scientific importance of the target. Alpha Centauri is not just any star system. It is the nearest star system to our own, the first place we might realistically hope to explore beyond the Sun. Any planets around these stars would be closer than any other exoplanets, easier to study, more compelling as potential targets for future missions. The intense interest in Alpha Centauri also creates pressure to report results quickly, which can conflict with the careful verification that science requires. The team balanced these pressures by publishing their findings as a candidate detection, clearly communicating both the exciting implications and the significant uncertainties. This transparency allows other researchers to evaluate the evidence and contribute their own analysis. Independent confirmation is the gold standard in science. If other teams using different instruments and methods can detect the same planet, the case for its existence becomes much stronger. Already, plans are underway for additional observations with Webb and other facilities. Over the coming years, a clearer picture should emerge. If the planet is confirmed, the implications are significant. It would be the first directly imaged planet in the habitable zone of a Sun-like star. It would be the closest exoplanet ever detected around a Sun-like star. It would demonstrate that the coronagraphic techniques developed for Webb work even in the most challenging circumstances. More broadly, confirmation would validate the strategy of searching for planets around the nearest stars. Some astronomers have argued that nearby stars have been oversearched, that the focus should shift to more distant systems, where survey telescopes can examine thousands of stars at once. The detection of a planet around Alpha Centauri A would justify the investment in high-contrast imaging of nearby targets, even if the candidate proves to be a false positive. The observations have value. They establish what Webb can and cannot detect around stars like Alpha Centauri A. They identify the sources of noise and systematic error that limit the sensitivity. They point the way toward improvements in technique and instrumentation that future missions might implement. Science advances regardless of whether individual results are confirmed or refuted. The process of testing hypotheses, gathering data, and refining understanding moves forward through both discoveries and null results. What matters is that the work is done carefully and the findings are reported honestly. The Alpha Centauri observations also highlight the complementary roles of different detection methods. The radial velocity technique excels at finding planets that orbit close to their stars, where the gravitational tug is strongest. The transit method finds planets whose orbits happen to carry them directly across the stellar disk. Direct imaging works best for planets that are widely separated from their stars, where they can be resolved against the coronagraphic residuals. Each method has its blind spots. Radial velocity misses planets on face-on orbits, where the stellar wobble is perpendicular to our line of sight. Transit observations miss planets on inclined orbits that never cross the stellar disk. Direct imaging misses planets too close to their stars to be resolved. A complete census of any planetary system requires applying multiple methods. For Alpha Centauri, radial velocity searches have been ongoing for decades. These observations have ruled out the presence of massive planets on short-period orbits, but lack the sensitivity to detect Earth-mass planets at Earth-like distances. The stellar activity of both Alpha Centauri A and B creates noise that obscures small signals. Transit searches have also been conducted, but with limited success. The precise alignment required for transits is rare, and neither Alpha Centauri A nor B is currently known to host transiting planets. Proxima Centauri B was discovered through radial velocity rather than transits, and subsequent searches have failed to detect transits of that planet. Direct imaging, now possible with Webb, fills in the gap. It can detect planets at orbital distances where radial velocity lacks sensitivity and where transits are geometrically unlikely. The candidate planet, at about 2 astronomical units from Alpha Centauri A, lies in precisely this regime, Chagre. Future missions will push all these methods further. The Roman Space Telescope will conduct wide-field surveys that could detect planets around thousands of nearby stars through microlensing and coronagraphy. The extremely large ground-based telescopes will achieve angular resolutions far exceeding what is possible today, enabling direct imaging of smaller and closer-in planets. Proposed space missions with specialized instrumentation could detect Earth-sized planets in the habitable zones of the nearest Sun-like stars. The technological progress in exoplanet detection has been remarkable. When the first exoplanet around a Sun-like star was discovered in 1995, it was a Jupiter mass object on a 4-day orbit, detectable only because its gravitational influence on the star was relatively strong. Today, we can detect planets smaller than Earth and image planets in the habitable zones of nearby stars. In another 30 years, we may be able to characterize the atmospheres of Earth-sized planets around the nearest stars. This progress has been driven by improvements in detectors, optical systems, data processing, and theoretical understanding. Infrared detectors have become more sensitive and less noisy. Optical systems have become more precise, with adaptive optics that correct for atmospheric distortion in real time, and coronagraphs that suppress starlight more effectively. Data processing algorithms have become more sophisticated, extracting faint signals from complex noise backgrounds. Theoretical models have improved our understanding of what signatures to look for and how to interpret them. The James Webb Space Telescope represents the current state of the art, but it is not the end of the road. Already, engineers and scientists are designing the next generation of instruments. Some of these will fly in space, beyond the blurring effects of Earth's atmosphere. Others will be installed on the extremely large telescopes now under construction, taking advantage of the vast light-gathering power of mirrors tens of meters across. One particularly ambitious concept is the Habitable Worlds Observatory, a proposed NASA mission that would be specifically designed to image and characterize Earth-like planets around nearby stars. This mission would carry a coronagraph optimized for extremely high contrast, capable of suppressing starlight by factors of 10 billion or more. At such contrast levels, Earth-sized planets in the habitable zones of the nearest Sun-like stars could be directly detected and studied. The Habitable Worlds Observatory is still in the conceptual phase, with launch not expected until the 2040s at the earliest. But it represents the direction the field is heading. The goal is not merely to detect exoplanets, but to characterize them in detail, determining their temperatures, compositions, and atmospheric properties. Ultimately, the goal is to find signs of life. Biosignature detection is the holy grail of exoplanet science. If we could identify chemical signatures in a planet's atmosphere that indicate the presence of life, it would be one of the most profound discoveries in human history. The challenge is distinguishing genuine biosignatures from abiotic processes that could produce similar chemical abundances. On Earth, the atmosphere contains oxygen at about 21% by volume, a concentration that would be difficult to maintain without the continuous production by photosynthetic life. The simultaneous presence of oxygen and methane is particularly telling, since these gases react with each other and would not coexist in equilibrium without ongoing replenishment. Detecting similar disequilibrium chemistry on an exoplanet would be strong evidence for biological activity. However, false positives are possible. Some models suggest that photochemical processes in certain types of atmospheres could produce oxygen without life. Water vapor split by ultraviolet radiation could release oxygen, which might accumulate if the planet lacks the geological processes that normally remove it. Interpreting any detection of oxygen or other potential biosignatures would require careful analysis of the planetary and stellar context. For the Alpha Centauri system, biosignature detection remains a distant goal. The candidate planet around Alpha Centauri A, if confirmed, is likely a gas giant without a solid surface, not a promising target for life as we know it. Proxima b is potentially rocky, but its atmosphere, if it has one, will be extremely difficult to characterize given the challenges of observing such a small planet around such a dim star. Yet the search continues because the stakes are so high. Finding life beyond Earth would answer one of the oldest questions humanity has ever asked. It would demonstrate that life is not a unique accident, confined to one planet in one solar system, but a natural phenomenon that arises wherever conditions permit. It would transform our understanding of biology, philosophy, and our place in the cosmos. Until that day comes, we content ourselves with the search. Each observation, each analysis, each incremental improvement in technique brings us closer to an answer. The candidate planet around Alpha Centauri A is one small step on a long journey, a journey that began when the first humans looked up at the stars and wondered what was out there. The night sky has not changed since those ancient days, not in any way perceptible to human eyes. The same stars that our ancestors saw continue to shine, tracing their slow paths across the celestial sphere. Alpha Centauri still gleams in the southern sky, the third brightest point of light in the heavens, beckoning us with its proximity. What has changed is our ability to understand what we see. Where our ancestors saw only points of light, we see stellar systems. Where they could only wonder, we can measure. Where they told stories to explain the heavens, we gather data and test hypotheses. The universe has not changed, but our relationship to it has been transformed. This transformation accelerates with each passing year. The technologies that make exoplanet detection possible, large mirrors, sensitive detectors, sophisticated optics, improve steadily. The computational tools that process vast datasets and model complex systems grow more powerful. The theoretical frameworks that guide observation and interpretation become more refined. In another century, our descendants may look back at our current efforts with the same mix of respect and bemusement that we feel toward Galileo's first telescopic observations. They may wonder how we managed to learn so much with such primitive instruments. They may be astonished that we ever doubted whether planets existed around other stars, or whether life might be found beyond Earth. But they will also recognize our work as the foundation upon which their knowledge is built. Every observation we make, every discovery we claim, every error we correct, becomes part of the scientific record that future generations inherit. The search for planets around Alpha Centauri is part of this ongoing human project, one thread in a tapestry that has been woven for centuries and will continue for centuries more. Tonight, as you settle into peaceful rest, the stars continue their vigil. They shine not for us, but because it is their nature to shine, converting hydrogen to helium in fusion reactions that have continued for billions of years. They know nothing of our curiosity, our hopes, our fears. They simply burn. And yet, from that burning, from those streams of photons crossing the interstellar void, we extract knowledge. Each photon that reaches our detectors carries information about its origin, encoded in its wavelength and intensity. By collecting enough photons, analyzing them carefully, comparing observations to models, we piece together a picture of the universe that no unaided eye could ever see. The candidate planet around Alpha Centauri A, if it exists, shines in the infrared, with a light too faint for any human eye to detect. Only through technology, through the accumulated cleverness of generations of engineers and scientists, can we perceive its glow. And yet, perceive it we do. Or at least we perceive something that might be it. A faint point of warmth against the background noise. Whether this particular detection proves real or illusory, the search will continue. Other observations will be made, other candidates identified, other analyses performed. Some will be confirmed as genuine discoveries. Others will be revealed as artifacts or misinterpretations. The process of science, patient and relentless, will sort the true from the false. In the end, we will know what planets orbit Alpha Centauri. We will know their masses and sizes, their orbital periods and eccentricities, perhaps even their atmospheric compositions and surface conditions. We will know whether any of them might harbor life, or at least whether any of them present conditions where life might be possible. This knowledge will not come quickly or easily. It will require decades of observation, improvements in technology that we can only dimly foresee, perhaps breakthroughs in understanding that no one has yet imagined. But it will come, because that is what science does. It answers questions, one observation at a time, one discovery at a time, one generation at a time. The stars wait, patient and eternal, and we reach toward them, curious and determined, knowing that the answers we seek are written in their light, waiting for us to learn how to read them. The universe speaks to us in light. Every star, every galaxy, every glowing cloud of gas and dust communicates across the void through photons that travel at the fastest speed nature allows. This light carries stories of birth and death, of creation and destruction, of processes that began before Earth existed and will continue long after our sun has faded to a dim ember. Alpha Centauri speaks to us across 4 light years, its messages arriving more than 4 years after they were sent. The light entering your eyes tonight left those stars when you were 4 years younger, living a different life, perhaps worrying about different things. The universe operates on timescales that dwarf human concerns, yet somehow we find ways to ask questions of these ancient, distant fires. The search for planets around our nearest stellar neighbor is part of a broader human endeavor to understand our place in the cosmos. For most of history, we assumed the universe revolved around Earth, that our planet held a special position in creation. Over centuries of observation and thought, this assumption crumbled. Earth became one planet among many, orbiting one star among billions, in one galaxy among trillions. This cosmic humility could be seen as diminishing, a reduction of human significance in the face of an indifferent universe. But it can also be seen as liberating. If we are not uniquely special by divine decree, then our significance must come from what we make of ourselves, from our choices and our creations, from the questions we ask and the answers we find. The search for exoplanets is one such choice, one such question. We look outward not because the universe cares whether we look, but because we care. We are curious beings, evolved to explore and understand our environment. The fact that our environment now includes the entire observable cosmos simply expands the scope of that ancient curiosity. Alpha Centauri represents the first step beyond our cosmic neighborhood. If we can learn what planets exist there, we will have extended our knowledge beyond the solar system in a meaningful way. Not just detecting distant points of light, but understanding them as worlds, places where certain conditions prevail, where certain things might be possible. The candidate planet detected by Webb, whether it proves real or not, marks a milestone in this journey. For the first time, we have pointed our most powerful instruments at the nearest sun-like star and seen something that might be a planet in its habitable zone. The technology works. The methods are valid. The questions are answerable, if not yet fully answered. This achievement rests on the work of thousands of people across decades. Engineers who designed and built the telescope, scientists who developed the observing strategies, technicians who assembled and tested the instruments, mission controllers who operate the spacecraft, analysts who process the data, theorists who model the expected signals. Each contributed a piece to the puzzle, and together they have created something no individual could accomplish alone. The collaborative nature of modern science is one of its greatest strengths. No single person can be expert in all the fields that contribute to a discovery like the candidate planet around Alpha Centauri A. The optics experts understand how to build coronagraphs. The detector specialists know how to extract faint signals from noise. The orbital dynamicists can model the motions of planets in complex gravitational environments. The astrobiologists consider what conditions might make a world habitable. Only by combining all this expertise can we hope to understand distant planetary systems. This collaboration extends across national boundaries. The James Webb Space Telescope is a partnership between NASA, the European Space Agency, and the Canadian Space Agency. Scientists from dozens of countries contribute to its observing programs. The knowledge it generates belongs to all humanity, not to any single nation or institution. The international nature of space science reflects something important about the questions we ask. The universe does not care about human borders. The laws of physics apply equally in every country. The stars shine on all people, regardless of nationality or creed. When we look outward, we are reminded of our common humanity, our shared curiosity, our collective place on a small world in a vast cosmos. This perspective can be humbling, but it can also be unifying. The challenges we face on Earth, climate change, resource depletion, conflict and inequality, seem more tractable when viewed from a cosmic vantage point. If we can build telescopes that detect planets around other stars, surely we can solve the problems that divide us here at home. The search for life beyond Earth adds another dimension to this perspective. If we find that life exists elsewhere, we will know that the processes which created us are not unique to Earth. The chemistry of life, the evolution of complexity, the emergence of awareness, all of these might be cosmic phenomena occurring wherever conditions permit. We would be not just one species on one planet, but members of a living universe. Even if we find that life is rare, confined to a few special worlds in a mostly empty cosmos, this knowledge would be valuable. It would highlight how precious our own world is, how important it is to protect the conditions that allow life to flourish here. It would underscore the responsibility we bear as the only known intelligence in the universe, or at least in our corner of it. The Alpha Centauri system offers no guarantees. It may contain habitable worlds, or it may not. The candidate planet around Alpha Centauri A may be a gas giant in the habitable zone, or it may be an artifact of the detection process. Proxima B may support a thick atmosphere and liquid water, or it may be a radiation-blasted wasteland. We do not yet know. What we know is that we are looking. We are asking the questions, gathering the data, testing the hypotheses. We are doing what humans have always done when faced with the unknown, exploring it. The Alpha Centauri system is just one target among many, but its proximity makes it special. Whatever we learn there will inform our understanding of planetary systems everywhere. The night grows deeper as Earth turns away from the sun. In the quiet hours before dawn, the sky displays its treasures most clearly. The Milky Way arches overhead, a river of light composed of billions of stars too distant to see individually. Among them, lost in the glow, are planets beyond counting, worlds we will never visit, perhaps worlds we will never even detect. But Alpha Centauri stands out. It is close enough to study in detail, to probe with our instruments, to imagine in concrete terms. When we think about interstellar travel, Alpha Centauri is invariably the destination. When we dream of finding another Earth, Alpha Centauri is where we look. It occupies a special place in our cosmic imagination, a beacon calling us outward. The dream of traveling to the stars is ancient. Long before we knew what stars were, humans told stories about journeys to the heavens. The desire to explore, to see what lies beyond the horizon, seems built into our nature. The stars call to us, and we respond with longing. Modern technology has brought that dream within reach, at least in principle. The breakthrough starshot concept shows how tiny spacecraft might be accelerated to a significant fraction of light speed, crossing the interstellar gulf in decades rather than millennia. Whether this particular approach proves practical or not, it demonstrates that interstellar travel is not forbidden by physics. It is merely very, very difficult. The difficulty should not discourage us. Every great achievement in human history seemed impossible before it was accomplished. Flight was impossible until it was not. Reaching the moon was impossible until it was not. Landing spacecraft on Mars, detecting gravitational waves, imaging black holes, all of these were once considered fantasies and are now accomplished facts. Interstellar travel may join this list someday. Not in our lifetimes, perhaps, but someday. And when it happens, Alpha Centauri will be where we go first. The observations we make now, the planets we detect, the conditions we characterize, all of this will inform the planning of that first mission. Our work today lays the foundation for journeys yet to come. For now, we travel to the stars through light alone. The photons that reach our telescopes have made the journey we cannot yet make ourselves. They carry the news of distant worlds, encoded in their wavelengths and intensities. By reading this light, we learn what lies beyond. The candidate planet around Alpha Centauri A, if it exists, is a world made of the same elements that compose Earth. Carbon, oxygen, silicon, iron, all the heavy elements forged in ancient stars and scattered through space by supernova explosions. The atoms in your body and the atoms in that distant world share a common origin in the nuclear furnaces of stars that died before our sun was born. This connection links us to the cosmos in a profound way. We are not merely observers of the universe, we are participants in it. The matter that makes up our bodies has cycled through stars and interstellar clouds, through planets and comets, through processes spanning billions of years. When we study a distant planet, we study our own cosmic ancestry, the story of how matter comes together to form worlds. The elements heavier than hydrogen and helium, everything from carbon to uranium, were created inside stars. When massive stars exhaust their nuclear fuel, they explode as supernovae, flinging these heavy elements into space. Over time, these elements mix with primordial hydrogen and helium to form new clouds of gas. When these clouds collapse under their own gravity, new stars and planets form, enriched with the products of earlier stellar generations. Our solar system formed from such a cloud about 4.6 billion years ago. The heavy elements that make up Earth, and ultimately that make up us, were already present in that cloud, contributed by stars that lived and died long before the sun ignited. We are, quite literally, made of stardust. The same process occurred in the Alpha Centauri system. The three stars there formed from their own cloud of gas and dust, enriched by their own stellar predecessors. Any planets around those stars are made of the same cosmic raw materials as Earth. The chemistry is the same, the physics is the same, the potential for complexity is the same. This universality of physics and chemistry is what makes the search for life elsewhere so compelling. If life arose on Earth through natural processes operating on common materials, then life might arise anywhere that similar conditions exist. The universe does not distinguish between one planet and another. The same laws apply everywhere. Of course, conditions matter enormously. Life requires energy, liquid water, and a suite of chemical elements in the right combinations. Not every planet provides these conditions. Most of the universe is hostile to life as we know it. Too hot or too cold, too dry or too toxic, too unstable or too energetic. Life clings to narrow margins where conditions happen to be favorable. Earth occupies such a margin. Our planet orbits at just the right distance from a just right star, with a just right atmosphere and a just right moon, stabilizing our axial tilt. Countless factors have combined to make Earth a haven for life. Whether these factors are common or rare in the universe remains unknown. Alpha Centauri offers a chance to explore this question. If we find that the nearest Sun-like star hosts a planet with conditions similar to Earth, it would suggest that such worlds are common. If we find that even this nearby well-positioned system lacks habitable planets, it would suggest that Earth-like worlds are rare. Either finding would have profound implications. The night deepens further, and the stars seem to brighten as the sky grows darker. In rural areas, far from city lights, the Milky Way becomes a luminous band stretching from horizon to horizon. Each point of light in that band is a sun, perhaps, with its own retinue of planets, its own possibilities for life. We will never know most of these distant worlds. They are too far, too faint, too lost in the cosmic multitudes. But we can know Alpha Centauri. It is close enough, bright enough, accessible enough. It is the place where our long isolation might first be broken, where we might first discover that Earth is not alone. As you drift towards sleep, let your thoughts wander among the stars. Imagine the light that has traveled 4 years to reach your eyes, the messages encoded in its wavelengths, the stories waiting to be told. Imagine a world orbiting a yellow star much like our sun, a world warmed by familiar light, a world where anything might be possible. The universe is vast beyond imagining, but it is not empty. It is filled with stars and planets, with energy and matter, with processes that have been unfolding since time began. We are part of this universe, made of its substance, governed by its laws, connected to its every corner by the common physics that binds all things together. Alpha Centauri is our nearest neighbor in this cosmic community. It has shone in Earth's sky since before there were eyes to see it, since before there was life to wonder at its light. Now, for the first time, we are learning what secrets it holds. The search for planets there continues, and with it, the search for answers to the deepest questions we can ask. Are we alone? Is Earth unique? What does the universe hold beyond the bounds of our small world? These questions have haunted humanity for as long as we have been human. Now, at last, we have the tools to seek answers. The answers may be years or decades away, but they are coming. Each observation brings us closer. Tonight, as consciousness fades and dreams begin, the stars keep their vigil. They do not sleep, do not rest, do not pause in their ancient burning. They will be there when you wake, shining as they have always shone, waiting for the questions we have not yet thought to ask. Alpha Centauri waits. The search continues, and somewhere in that distant light, perhaps, a world awaits discovery, a world that will change everything we think we know. The universe is patient, so must we be. The stars call to us across the void, and we answer with our instruments and our curiosity, our dreams and our determination. The journey to Alpha Centauri has already begun, not in spacecraft, but in light, in data, in the slow accumulation of knowledge that will someday carry us to the stars. Rest now beneath the watchful eyes of 1 billion suns. Dream of worlds beyond counting, of journeys beyond imagining, of answers that lie hidden in the light. The universe keeps its secrets, but not forever. One day we will know. One day perhaps we will go. Until then, the stars shine on, ancient and patient and full of wonder. And we, the curious creatures who have learned to read their light, continue the search, continue the dreaming, continue the long, slow reach toward the infinite. Good night, Voyager. The cosmos awaits. There is something deeply human about looking up at the night sky and wondering. Before we had language to express our questions, Before we had science to seek answers, we looked up. The stars were there, mysterious and unreachable, inviting contemplation. Our ancestors named the patterns they saw, told stories about the lights in the darkness, imagined gods and monsters dwelling among the celestial fires. We have come far from those ancient nights, yet the fundamental impulse remains the same. We still look up. We still wonder. The questions have grown more precise, the tools more sophisticated, but at the core, we are still those early humans, gazing at the night sky and asking what lies beyond our small circle of firelight. Alpha Centauri would have been visible to our ancestors, at least to those who lived in the southern parts of Africa, Asia, and beyond. They would have seen it as a bright point of light, not knowing it was 3 stars bound by gravity, not knowing it harbored planets, not knowing it was so relatively close to Earth. They could not have imagined that their descendants would build instruments capable of detecting worlds around that distant beacon. The journey from those first wanderings to our current capabilities spans thousands of generations. Each generation added something, a new observation, a new idea, a new technology. The ancient Greeks measured the Earth's circumference. Medieval scholars preserved and transmitted astronomical knowledge. Renaissance astronomers developed the heliocentric model. Newton's laws explained the motions of planets. Einstein's relativity refined those laws for extreme conditions. Each step built on what came before. The pace of discovery has accelerated dramatically in recent centuries. The time between Galileo's first telescopic observations and the launch of the James Webb Space Telescope spans just 4 centuries, a blink of an eye in cosmic terms. In that brief interval, we have gone from not knowing that the Milky Way consisted of individual stars to detecting planets orbiting those stars. The change is staggering. This acceleration shows no signs of slowing. The next few decades will bring telescopes larger than any yet built, both on the ground and in space. These instruments will peer deeper into the universe and resolve finer details than anything we can achieve today. The search for exoplanets will extend to smaller, cooler, more Earth-like worlds. The characterization of their atmospheres will become routine rather than exceptional. For Alpha Centauri specifically, the coming years promise answers. The candidate planet around Alpha Centauri A will either be confirmed or ruled out as more observations accumulate. The atmosphere of Proxima b will eventually be characterized, revealing whether that world has retained any atmosphere at all. The question of whether habitable planets exist in our nearest stellar neighborhood will be answered one way or another. Whatever the answers, they will not be the end of the story. Science does not reach final conclusions, only better approximations. Each discovery raises new questions. Each answer reveals new mysteries. The search for understanding is endless, which is part of what makes it so compelling. The specific question of life around Alpha Centauri is particularly poignant. We have evolved on a world teeming with life, surrounded by countless organisms that share our common ancestry. Every creature on Earth, from bacteria to blue whales, descends from the same original cells that somehow emerged from chemistry billions of years ago. We know life can exist because we are life, but we do not know if life exists elsewhere. Despite decades of searching, we have found no definitive evidence of life beyond Earth. No radio signals from alien civilizations, no biosignatures in the atmospheres of other planets, no fossils on Mars or microbes in the ice of Europa. The universe remains, as far as we can tell, silent. This silence could mean many things. Perhaps life is rare, requiring conditions so specific that Earth is the only place in the visible universe where it has arisen. Perhaps life is common, but intelligence is rare, with most biospheres remaining at the microbial level for their entire histories. Perhaps intelligent civilizations arise but destroy themselves quickly, leaving no lasting signals. Or perhaps the universe teems with life, but we have not yet developed the technology or the luck to detect it. Alpha Centauri cannot answer all these questions, but it can answer some. If we find that even the nearest Sun-like star lacks habitable planets, it suggests that Earth-like worlds are rare. If we find habitable planets but no signs of life, it suggests that the conditions for life are not sufficient to guarantee its emergence. If, against all odds, we detect biosignatures around Alpha Centauri, it would be the most significant discovery in the history of science. The search carries risks of disappointment. We might find nothing, or we might find worlds hostile to life, or we might find ambiguous signals that take decades to interpret. Science rarely provides the dramatic revelations that fiction imagines. More often, it offers slow, incremental progress, punctuated by occasional leaps forward. But even slow progress is progress. Each observation of Alpha Centauri, whether it yields exciting results or null results, adds to our knowledge. Each improvement in technique, each refinement in analysis, each theoretical advance brings us closer to understanding. The goal is not immediate gratification, but eventual comprehension. This long view is essential for those who work on problems that span generations. The astronomers who planned the James Webb Space Telescope in the 1990s knew they would not see its first images until decades later. Many did not live to see the launch, yet they worked on, knowing that their contributions mattered, that the science would continue, that future generations would build on what they started. The same spirit animates the search for exoplanets around Alpha Centauri. Those working on this problem today may not see its ultimate resolution. The answer might come in 10 years or 50 years or 100 years. But the work continues regardless, each researcher contributing what they can, each observation adding to the cumulative record. This intergenerational effort is one of humanity's most admirable qualities. We are capable of working toward goals that benefit not ourselves but our descendants. We plant trees whose shade we will never enjoy, build cathedrals whose completion we will never see, ask questions whose answers we may never know. This capacity for long-term thinking elevates us beyond our immediate circumstances and connects us to the future. The stars embody this long view. They burn for billions of years, their light reaching us across centuries and millennia. When we study a star like Alpha Centauri, we are not just observing a point of light, but engaging with a process that began before Earth formed and will continue long after humanity is gone. The stars put our brief lives in perspective, reminding us of the vastness of time and the continuity of the cosmos. Yet, within that vastness, our moment matters. We are the first generation with the capability to detect planets around other stars, the first generation that might answer the ancient question of whether we are alone. This privilege carries responsibility. We must do the work well, ask the right questions, gather the best data, and pass on our findings to those who follow. The candidate planet around Alpha Centauri A represents one small piece of this larger project. It may prove to be a real world or a mirage of the data. Either way, the observation has value. It tests our methods, refines our techniques, and moves us closer to the day when such detections become routine. In the quiet hours of the night, when the mind grows still and the world fades to dream, the stars continue their ancient watch. They do not know that we are here, that we observe them, that we wonder about them. They simply burn, as they have burned for billions of years, as they will burn for billions more. But we know, we are aware, we are curious, we are reaching out. From our tiny world, orbiting an ordinary star, we send our questions into the cosmos. Most of those questions will never be answered, but some will be, and each answer changes us a little, expands our understanding, deepens our connection to the universe that created us. Alpha Centauri is part of that connection. It is the nearest rung on the cosmic ladder, the first step beyond the familiar. What we find there, or do not find, will shape how we think about all the other stars, all the other planets, all the other possibilities that the universe contains. The search continues because searching is what we do. We are explorers by nature, question askers by disposition, dreamers who reach for the unreachable. The stars call to us, and we answer. We build our telescopes, gather our data, analyze our observations, and slowly, patiently, we learn. Tonight, Alpha Centauri shines in the southern sky, as it has shone for as long as there has been an Earth to see it. The light that left those stars 4 years ago is arriving now, carrying information about worlds we are only beginning to understand. In that light are answers to questions we have asked for millennia. The journey to the US stars has begun. Not in rockets and starships, but in light and data, in questions and answers, in the patient work of understanding. One day, perhaps, our descendants will make the journey in person, crossing the void that separates us from our nearest neighbors. When they do, they will carry with them everything we have learned, every observation we have made, every insight we have gained. We are laying the groundwork for that future, brick by brick, observation by observation, discovery by discovery. The work is slow, the progress gradual, the answers elusive. But the work continues, and with it, the eternal human project of understanding where we are and what lies beyond. Rest now, beneath the stars. Let your breathing slow, your thoughts quiet, your consciousness drift towards sleep. The universe will still be there when you wake, vast and ancient and full of wonders. Alpha Centauri will still shine, patient and bright, waiting for the questions we have not yet thought to ask. The cosmos does not hurry, neither should we. The answers will come in their own time, revealing themselves to those who look with patience and persistence and wonder. The search for worlds around our nearest star is part of this timeless endeavor, one thread in the tapestry of human curiosity that stretches back to the first minds that looked up and wondered. Sleep well, fellow traveler. The stars keep watch while you dream, and somewhere out there, perhaps closer than we know, worlds await discovery, mysteries await solution, answers await the questions that will unlock them. The night is long, but not eternal. Dawn will come, bringing new light, new observations, new chances to understand. Until then, rest in the knowledge that you are part of something larger than yourself, a species that asks questions of the cosmos and sometimes hears answers in return. Alpha Centauri shines on, the search continues, and the universe, patient as always, waits for us to find what it has hidden in the light. The tools we use to study the stars have transformed beyond recognition in the span of a single human lifetime. Those born in the middle of the 20th century witnessed the transition from photographic plates to digital detectors, from ground-based observatories limited by atmospheric blur, to space telescopes with crystalline clarity, from indirect methods that inferred planets from stellar wobbles, to direct imaging that captures their light. This technological revolution continues to accelerate. The James Webb Space Telescope represents the current pinnacle, but it will not remain so for long. Even as Webb observes Alpha Centauri and other nearby systems, engineers are designing its successors. Larger mirrors, more sensitive detectors, more sophisticated coronagraphs, all are under development. Each advance opens new windows on the cosmos. The extremely large telescopes now under construction in Chile and Hawaii will dwarf anything that has come before. The European Extremely Large Telescope will have a primary mirror 39 meters across, gathering more light than any telescope in history. The giant Magellan Telescope and the 30-meter telescope will be nearly as capable. Together, these giants will transform ground-based astronomy. For exoplanet science, these telescopes offer tantalizing possibilities. With adaptive optics that correct for atmospheric turbulence in real time, they may be able to directly image planets around nearby stars that are currently beyond reach. The angular resolution of a 39-meter telescope far exceeds anything in space, allowing finer details to be resolved. If Earth-like planets exist around Alpha Centauri, these telescopes may be the ones to find them. Space-based missions also continue to advance. The Nancy Grace Roman Space Telescope will carry a coronagraph instrument specifically designed for exoplanet imaging. While its primary mirror is smaller than Webb's, its coronagraph incorporates technologies that promise higher contrast and smaller inner working angles. Roman may see planets that Webb cannot. Beyond Roman, more ambitious concepts are under study. The Habitable Worlds Observatory, if approved and built, would be specifically designed to image and characterize Earth-like planets around nearby Sun-like stars. Its coronagraph would achieve contrast ratios of 10 billion to 1, suppressing starlight to levels where Earth twins become visible. Such a mission could definitively answer whether habitable planets exist in our cosmic neighborhood. The timeline for these future missions stretches over decades. Roman is scheduled for the late 2020s. The Habitable Worlds Observatory, still in the conceptual phase, would not launch until the 2040s at the earliest. The extremely large telescopes are expected to see first light in the late 2020s and early 2030s. Each milestone brings new capabilities, new discoveries, new questions. For Alpha Centauri specifically, this progression of instruments offers hope. Even if current observations cannot definitively confirm or rule out planets, future instruments may succeed. The candidate planet around Alpha Centauri A might be confirmed by Roman's coronagraph or the extremely large telescopes. Smaller planets not yet detected might reveal themselves to more sensitive searchers. The atmosphere of Proxima b might yield its secrets to specialized spectrographs. The key is persistence. Exoplanet science rewards those who return to targets again and again, gathering data over years and decades. The radial velocity method that found Proxima b required years of observations to tease out the planetary signal from stellar noise. Direct imaging campaigns similarly benefit from repeated observations that can distinguish real planets from transient artifacts. The research team that detected the candidate planet around Alpha Centauri A plans exactly this kind of persistent campaign. They will observe again and again, at different times and with different configurations, building up a dataset that can definitively establish whether the candidate is real. This work will take years, but that is how science advances. The patience required for such work mirrors the patience required by the universe itself. Stars burn for billions of years. Planets orbit for eons. Life, if it exists elsewhere, has had time beyond human comprehension to emerge and evolve. Against these timescales, a few decades of careful observation is nothing. Yet to the humans involved, these timescales are everything. A scientist's career spans perhaps 40 or 50 active years. Many of those working on Alpha Centauri today will not live to see the final answers. They work anyway, contributing what they can, trusting that others will carry on. This intergenerational commitment is the true measure of scientific culture. We do not work only for ourselves, but for those who will come after. The observations we make, the methods we develop, the questions we ask, all become part of a legacy that extends beyond any individual life. Science is a relay race, each generation passing the baton to the next. The baton we pass forward includes everything we have learned about Alpha Centauri, the stellar properties of the three stars, their masses and luminosities and chemical compositions, the orbital dynamics of the binary pair and their distant red dwarf companion, the confirmed planets around Proxima Centauri and the candidate planet around Alpha Centauri A, the constraints on what planets might exist and where. All of this knowledge accumulates, forming the foundation for future discoveries. As the night deepens and sleep approaches, these thoughts can accompany you into dreams. The universe is vast, yes, but it is also knowable. Piece by piece, observation by observation, we are mapping its contents and understanding its processes. The stars that seem so mysterious to our ancestors are becoming familiar, their secrets slowly yielding to our instruments and our intellect. Alpha Centauri is part of this grand project of understanding. It is the nearest piece of the cosmic puzzle, the closest example of what the universe contains beyond our own solar system. What we learn there illuminates what we might find everywhere. The stakes are high, the challenge is immense, the rewards beyond measure. So rest now, knowing that the search continues. Somewhere, telescopes are gathering light from distant stars. Computers are processing data, searching for signals. Scientists are analyzing results, testing hypotheses, refining theories. The work goes on day and night, year after year, generation after generation. And Alpha Centauri shines on, patient and eternal, waiting for us to discover what it has to show. 4 light years away, but closer with every observation. Mysterious still, but less so than before. Our nearest stellar neighbor, holding secrets we are only beginning to unravel. The journey continues, the stars await. And we, the curious inhabitants of a small blue world, reach outward toward infinity, one photon at a time. The human mind, evolved on the savannas of Africa, was not designed for contemplating interstellar distances or billion-year timescales. Yet here we are, reaching beyond our evolutionary origins to ask questions that our ancestors could never have imagined. This capacity for wonder, for abstraction, for curiosity that transcends immediate survival needs, may be our most remarkable trait. When you look at Alpha Centauri, you are exercising this capacity. You are connecting with something vast and ancient, participating in a tradition of skywatching that stretches back to the first minds capable of wonder. The stars that shone on Paleolithic hunters shine on you tonight. The same light, traveling the same void, speaking the same cosmic language. We are the universe becoming aware of itself, as the great astronomer Carl Sagan once said. Through us, the cosmos contemplates its own existence, wonders at its own vastness, seeks to understand its own nature. This is no small thing. In all the universe we have explored, we have found no other minds asking these questions. We may be alone in our wondering, or we may have company waiting to be discovered. Either way, the questions themselves are precious, Alpha Centauri holds some of those questions, and perhaps some answers. It is the nearest place we might look for other worlds, other possibilities, perhaps other life. The search that Webb has begun will continue with future instruments and future generations. Someday, we may know what lies in that nearby stellar system, as well as we know our own solar neighborhood. Until that day, we observe, we analyze, we speculate, and we dream. The stars do not hurry, and neither should we. The answers will come when they come, revealing themselves to patient seekers who look with care and wonder. Let the rhythm of your breathing slow. Let your thoughts drift like starlight. The universe holds you as it holds all things, gently and eternally, without judgment or demand. You are made of stars returning each night to gaze at your cosmic kin. Alpha Centauri shines on. The search continues, and in the space between stars, possibilities await. Sleep well, Voyager. The cosmos keeps watch.